Bismillahirrahmanirrahim. Firstly, I want to thank the University of Ouargla for giving me an opportunity to participate in this international conference on sustainable energy and advanced materials. Dear students, professor, and everyone who listened to me, today I want to present my participate title by Vector Control of Double-Fed Indication Generator presented by Arabi Rahma. In the end, I hope that you will benefit and that it will not burning. Without longing, we start with the blessing of good. We have a plan of the work. Firstly, we show an introduction. Secondly, the modeling of the fish. Thirdly, vector control of double-fed indication generator. Then simulation and interpretation of the results. Robustness tests. At the end, we have a conclusion. 1. Introduction. Today, the development and proliferation of wind turbines have led research in electrical engineering to carry out investigation in order to improve the efficiency of the electromechanical conversion and the quality of the energy supplied. It is in this context that this dissertation that I am presenting to you describe a study on the use of asynchronous machine in a wind power system. In the case of Algeria, as shown in Figure 1, mapping the average annual recoverable power density at 10 meters, mass of the Southeast Sahara, is characterized by an average annual recoverable potential varying from 1 to 2 MWh per meter square. 2. Modeling of double-feed induction generator. The modeling of double-feed induction generator is described in the Park reference system. The following system of equations describe the overall modeling of the generator. 1. Electrical equation. This is equation on stator and rotor. 2. Magnetic equation. This is magnetic equation on rotor and stator. 3. Equation of the couple, COM. 3. Vector control of double-feed induction generator. Shows of reference from the double-feed induction generator model with stator flow orientation. The stator flow is oriented along the axis so that the component following the q-axis is constantly 0. So, phi ks equal to 0, phi ds equal phi s. Figure 1. This figure shows the orientation of the axis on the stator flow. Expression of the powers. We have got two powers, power active and power reactive. Expression of the flow on rotor and flow on stator, flow Ks equal to 0. Expression of the voltage on rotor and voltage on stator, Vds equal to 0, Vks equal to Vs. Expression of the currents, ETS and EQS. The system check must therefore take this error into account. Equation allow also established the block diagram of the double-feed induction generator electrical system to be regulated. Figure 2. Figure 2 shows the block diagram of the system to be regulated. The coupling terms are designated by V2, V3 and the FOMs by V1 and V4. FOM means la force électromotrice en français. Note that the power and the voltage are linked by a transfer function of the first order. In addition, due to the low value on this flip G, it will be possible to establish a vector control without difficulty Because the influence of the coupling will remain weak and the D and Q axis can therefore be controlled separately without our regulator. There are two solutions for controlling the power on this machine. The first method consists in neglecting the coupling term and setting up an independent regulator on each axis to independently control the active and reactive powers. This method will be called direct control because the power regulators directly control the rotor voltage of the machine. The second method consists in taking into account the term of coupling and to compensate them by carrying out a system comprising two loops, making it possible to control the power and the rotor current. This method called indirect control. Figure 3 shows the block diagram of the direct vector control and Figure 4 the block diagram of the indirect vector control. The LLTFR FTBL fonction de transfert en boucle ouverte en français. Open loop transfer function with the regulator is written as follows. It is the function of LTF, which gives us as a closed loop LTFC, loop transfer function closed. For a response time to 5% equal to 1 millisecond, we obtain Kp equal to 0.7575 asterisk 10 centimeters, Ka equal to 53.5456 asterisk 10 centimeters. Simulation and interpretation of the result. We started with the direct control. Figure 1 obtained the direct control of active and reactive power. We have got the power pursued in active power and the coupling between P and Q, active and reactive power. Then, Figure 2 obtained the result of direct control of stator and rotor current. We have got the increase of the current. Secondly, we have indirect control. Figure 3 obtain the result of indirect control of active and reactive power. Figure 4 obtain the result of indirect control of stator and rotor current. Robustness tests. The robustness test consists in varying the parameter of the double feed induction generator model used. In fact, regulator calculations are based on transfer function, the parameter to be fixed. Effect of variation of electrical parameters in direct control. Figure 5 obtain the influence of the variation of the rotor resistance RR of the plus 50% and Figure 6 obtain the influence of the variation of mutual inductance Lm of the minus 20% in power active and reactive. Then the Figure 7 obtain the influence of the variation of stator inductance Ls of minus 20% and Figure 8 obtain the influence of the variation of the rotor inductance Ll of the minus 20% in power active and reactive. Secondly, the effect of variation of electrical parameter on indirect control. Figure 9 obtain the influence of the variation of rotor resistance Rr of plus 50% and Figure 10 obtain the influence of the variation of the mutual inductance Lm of minus 20% in power active and reactive. Then the Figure 11 obtain the influence of the variation of l'inductance rotorique de minus 20% and Figure 12 obtain the influence of the variation of l'inductance rotorique de minus 20% in power active and reactive. At the end, we have a conclusion. In this article, we have developed the power vector control methods of the double-high-fed induction generator. First method, the direct control. We have indeed seen that a direct control is the easiest to implement, but not the most efficient. On the other hand, the indirect method allows us, in association with the power loops, to have a powerful and robust system. It is certainly more complex to implement, but will allow optimal operation of the electricity generation system while minimizing any concern related to the variation in the parameters of the machine and the wind power system. The synthesis of the PI regulator used to stabilize the system because of its speed and simplicity allowed us to determine the time constant necessary for the choice of these components. Thanks for attention.